Young friends, this will be the last lecture in this lecture series, and in this lecture I am going to review modules 6 to 9. The previous 5 I have quickly reviewed in the last 2 lectures. I have to rush through the main points in these modules because there was so much that I discussed. But there are certain points I would like to emphasize, and I would like to take that you take note of the following. In module 6, our learning objectives was to know about the complex nature of sulfides, learn about the pyrometallurgical extraction processes for a few metals, then the hydrometallurgical extraction processes, and a very important concept called process fuel equivalent. I mentioned there are many methods of metal recovery, and these methods involve thermal decomposition, roasting, subsequent reduction, control roasting. And in this I must mention that in the case of copper metallurgy, we talk about a phase which does not appear in other places. It is a matte. Matte is a mixture of sulfides. In copper metallurgy, we start with a sulfide concentrate from which we remove iron, most of the iron is iron oxide, and finally, we are left with a mixture of copper sulfide and iron sulfide, that is called matte. It does not need reduction. By controlled oxidation, once we go to remove FeS, then we start oxidizing copper sulfide, then there is a reaction between Cu2s and copper oxide and copper sulfide, and copper comes out. That is what happens during converting. I mentioned the pyrometallurgical steps in extraction of copper. In the conventional route, there are lots of operations. We have roasting, then reverberatory smelting, converting. These are combined in the flash smelting process. Roasting and smelting are combined. When you go for continuous copper, then all 3 steps are combined. So, when steps are combined, your energy requirements become less. In the sense, the steps are exothermic, but if you have too many steps, too many reactors, then a lot of heat losses. But when you combine steps from the energy point of view, it is better, and also the exhaust gases come out in concentrated streams. So, it can go for acid recovery. Then we went through what happens during copper. The problem during roasting of copper sulfide is that if you try to roast copper sulfide, copper will not form the oxide until iron forms oxide, because affinity of iron towards oxygen is more than affinity of copper towards oxygen. And yet, if we allow too much of oxidation of iron, then slagging would be difficult. So, idea would be to take it only to FeO stage, which can be removed. So, we ensure that Fe does not go into the higher oxides, and that is why we leave some FeS behind, and we get a matte which goes subsequently for smelting operation and converting. The final reaction is very interesting reaction. When we are left, we have a reaction Cu2s plus 2 Cu2O 6 Cu Once the matte is oxidized and we have twice as much Cu2 than Cu2s, then there is a suddenly reaction between the two and copper comes out. So, all the reactions are actually oxidation reactions in the case of copper. We are not reducing anything anywhere, and that is why we can think of combining. These are the conventional reverberatory smelting furnace, that it can be an electric smelting furnace. Finally, there is converting in a side blown converter. We cannot blow from the bottom. I have discussed exactly what happens when the converting reaction takes place. I have talked about copper loss in slag. and which is related to percentage copper in reverberative furnace matte. Then there was a discussion on fire refining of copper, because the blister copper that comes has many impurities and there are many pyrometallurgical steps to finally get copper, but finally you will get an impure copper, and that needs electrorefining. In the process of electrorefining, it releases as slimes or sludge at the bottom of the anode a solid residue which has all the precious metals. Some impurities that dissolve in the electrolyte are to be rejected. Essentially, in electrorefining, copper moves from impure anode to a pure cathode. The slimes is a source of many important byproducts, and we go through elaborate steps, chemical steps to remove them one by one. We get silver, we get tellurium recovery, we can get lead, we can get selenium. These are all very standard steps that have evolved over centuries of trial and error. Of greater interest in copper metallurgy is how we are combining reverberatory, smelting, converting, and before that roasting all in one in continuous copper making processes. In processes like flash smelting, roasting and smelting are combined. Converting is not done, and there are different designs of reactors, but then there are also newer processes where all three are combined, that we have roasting, smelting, converting in one furnace, and there are different kinds of furnaces. The main feature of these furnaces will be that since from roasting to converting, partial pressure of oxygen has to gradually increase. In the same reactor, there will be different zones where partial pressure of oxygen will be different. The other feature is there is always counter current flow of matte and slag. So, all these designs have been discussed, and I have shown how these counter current flow. The concept of process fuel equivalent, to which I am coming quite frequently, is very important. It is vital for analyzing any metallurgical step. The process fuel equivalent PFE is the quantity of fuel directly consumed by the process, fuel equivalent of electricity that we may be using in the process. So, these are the energy inputs. There is also another parameter S, which is the fuel equivalent of major supplies. The input materials have also required some power, energy when they were produced. So, that has to be taken into account. From that, we take away the fuel equivalent of byproducts and useful surplus heat. Very often we tend to forget the S term, that after all the raw materials that we use also have required energy for their production. So, only using such a term can we look at the energy equivalent. We have talked about hydrometallurgy of copper, where the copper sulphide is roasted to copper oxide and taken into solution, and then once we have a solution, we go for electrolysis and electrorefining. There is also bacterial leaching. In the case of copper ores, some bacteria help take copper into solution, but that takes long time. It is ideally suited for low grade ores. Extraction of lead is relatively a simple pyrometallurgical step. Lead sulphide concentrate is oxidized, or rather which is done in a sintering machine to produce lead oxide sinters. We need sinters because they must be hard, they have to go into the blast furnace. This blast furnace is shorter in height and it operates at a maximum the earth temperature is not as high as that in iron blast furnace. It is around 1000 degrees, and it is straight simple PbO being reduced by coke to produce lead. That lead is called lead bullion. Of special importance is the question of lead fumes coming out from the top, which could be very poisonous. So, they have to be trapped in special filter bags, and that is why I have shown one drawing of that. In the case of lead, there is a very elaborate process of refining of the lead bullion. Now, here initial step is aims at producing lead in a bulk form, all recovery, maximum recovery, but the impurities also come, and then only after we have produced lead in a bulk form called lead bullion, that we take the bullion and then go through various steps for taking out important byproducts. One of the very important byproducts is silver, and for silver removal there is a standard process in pyrometallurgy called Parkes process. When in the molten state, if you add zinc, zinc dissolves gold as well as other precious metals, and that forms a crust that can be removed, and then there are other processes, steps for removal of other things. People have tried to think of avoiding a complicated flow sheet and have tried to produce lead in one step continuous smelting process as we have for copper, but this has not become so popular as yet. Zinc is of particular interest to us because it was produced for the first time in India. The problem in reducing zinc oxide by carbon is that zinc comes out as a vapor. So, we need to have condensers. In India in ancient times, we had the vertical condensers as well as horizontal condensers. That is a pyrometallurgical extraction, but today hydrometallurgical extraction has become much more important, where we take zinc into solution after roasting and calcination. The solution goes through very elaborate purification process, because unless the solution is very pure, it will not be possible to electrolyze zinc, because we have to depend on activation over potential to ensure that hydrogen potential becomes more than the zinc potential. That is why zinc can be displaced. Normally, zinc will displace hydrogen from acid solutions, but because of activation over potential, which would be created when a current is being passed, zinc can be taken out of zinc solution. There is another important point, that when we are roasting zinc sulphide concentrate, one has to avoid formation of zinc ferrite, which cannot be leached. So, in extractive metallurgy of zinc, the formation of zinc ferrite is a very important subject. Then there is the modern process, where we again go back to pyrometallurgy, and the process called imperial smelting process can simultaneously produce by a pyrometallurgical reduction in a blast furnace both lead and zinc. Lead will come out from the bottom as it is, zinc will come out at the top as a vapor. Then in imperial smelting process, they have the method of dissolving the zinc vapors in a spray of molten lead to form a zinc lead alloy, and when that alloy is cooled, zinc separates out according to the phase diagram, and that lead will be recirculated. It is a very tricky process, but that is the basis. Another interesting subject is recovery of zinc by zinc slag fuming. In many lead slags, zinc will be there. There is a process called the fuming process for recovery of zinc. I have discussed what are the steps in the process we follow in production of zinc in Udaipur. Initially, the company was Udaipur Zinc Limited. Now, it has been privatized, and the company which is producing zinc is called Sterlite. The ores first produce a concentrate rich in zinc, then there is a roasting of the concentrate to convert zinc to soluble form. Then there is a zinc sulphate solution which is purified, and that from that zinc is obtained by electrolysis. This zinc is very, very pure, better than 99.99%, more than what we require for galvanizing, but we have to have pure solution. That is why we get very pure zinc, whether we like it or not. The concentrates also go to another place near Chittor in Rajasthan, where the imperial smelting process operates. I have talked about extraction of nickel. We are not extracting nickel in India, but we have chromite mines which produce an overburden that is accumulating, that has 0.6 to 0.8% nickel. And although we have had lot of R&D work, and we have even run pilot plants for recovery of nickel from that overburden, till today we do not have a commercial process. Nickel comes from both oxidic sources. The chromite overburden is an oxidic source, but in some countries nickel also is found along with some sulphide ores that contain copper also. There a matte route would be followed. I would avoid the going into the details of those. In module 7, we discussed extraction of metals from halides, and I made a distinction between halides that are in nature, like magnesium chloride, sodium chloride in seawater, or magnesium chloride in some deposits which are found on sea beaches, exposed seabeds. These are natural halides, but I also talked about extracting metals from halides that are produced from oxides. I put them in this module because even though we have oxides of titanium or uranium or thorium, we do not directly go from there to the metal. We have to first convert the oxides to pure halides, and from there we will obtain the metal. So, that is why we have put it in this category. We talked about the importance of halide metallurgy, made the distinction between naturally occurring halides and halides produced from oxidic ores. Then we have gone into discussing nuclear metals and non-nuclear metals from halides. Uranium, plutonium, thorium are nuclear metals which produce energy through fission reactions. Zirconium and beryllium are not fissionable metals, but they are vitally important in nuclear reactors. Then I have ended by discussing production of magnesium and sodium. All these ores of uranium or thorium, they are kind of low grade. So, always we have a low grade complex ore that needs upgradation through various techniques, and the idea will be to first finally produce a pure intermediate, an halide or an oxide from which we will get the metal. I have not gone into the details of how to produce the concentrates and produce the oxide. I have talked about leaching of the oxides, concentrates either by acids or by alkali, and then from the purified starting material we can chlorinate to produce a chloride from which we will get the metal, or we can also fluorinate. In the case of very stable oxides, I mentioned that you need presence of carbon for chlorination. Without carbon, they cannot be chlorinated. Carbon is a kind of reducing agent, which we can visualize that carbon first reduces the metal oxide, and then the metal reacts with chlorine to produce the vapor. We have talked in detail about various metallothermic reactions. We can use metals which produce very stable halides or oxides, generally it is calcium or magnesium. We go for this route, metallothermic reduction, for some advantages which are listed, that if we are going for metallothermic reduction of halides, then we have an oxygen free reaction. So, the metal produced does not get reoxidized, we get a superior product. But the choice of metallothermic reduction depends on a number of factors. First of all, the feasibility in terms of free energy change in the reaction, in terms of enthalpy change, so that we can tell whether the reaction itself is making available sufficient heat. If not, we have to have a booster reaction, we have to put in another reaction that gives us supply heat. We have to worry about the melting points and boiling points of reactants and products to see whether it allows easy handling or it is possible to do things under normal conditions. We also have to worry about separation of metal and slag for cleaner recovery. I went into a good bit of discussion on how we get nuclear energy. The vital element is uranium. Without uranium, we cannot have a nuclear energy program. Uranium has 3 isotopes, of which only U-255 is fissionable. There is one U-34 which is so small in percentage you can ignore. U-238 is not fissionable, but we call it a fertile material, because it can be converted to a fissionable element, plutonium-239. So, from uranium we are getting a fissionable isotope and a fertile isotope, which gives plutonium-239. Another isotope of uranium can be produced by neutron irradiation of thorium, thorium-232, which will give uranium-233. That would be the most promising starting material for nuclear energy. Why? Because per neutron absorbed, uranium-233 produces more neutrons as compared to the fission of plutonium or uranium-235. This is called eta value, that number of neutrons emitted by a fissile nucleus per neutron absorbed. For U-233 is 2.3, for U-233 is 2.06, U-239 2.06. Now, the point to note is all the uranium-235, 239, sorry, plutonium-239 comes from uranium-238 by this reaction. It does not mean that all of uranium-238 will give rise to plutonium. As a matter of fact, only tiny fraction of uranium-235 will give uranium-239, and there has to be elaborate chemical steps and chemical engineering steps for recovering it from a huge irradiated mass. But we now have methods of those. A very key thing is separation of the isotopes, and I have talked about centrifuging and gas diffusion. These two will separate uranium-235 from uranium-238, because their atomic weights are different. In gas diffusion, the idea is to have a gas supply which has both the isotopes in the form of volatile compound. All the molecules are moving all over the place, but the lighter isotopes are likely to impinge on a membrane more frequently and therefore escape. So, from the other side of the membrane we get an enriched material which has more U-235 as compared to U-239. This is one way. Then I have talked about the way we are treating uranium ore in Jaduguda mines. We are starting from something which is 0.08% U3O8. See how lean the ore is. But yet from that we go through various steps to produce a concentrate which is 70% U3O2, and only when you have that again further purification will produce a pure oxide. From that we can produce a fluoride or chloride, and then we can think of reducing by some metal the oxide or the fluoride. There we have to take into account where free energy change is more, where the enthalpy, the exothermic heat available is more, and of course, the physical conditions of the reducing reductant product, etc. I mentioned that when a reaction is not feasible, we can drive it to the right by either dissolving the metal in the form of an alloy or taking out the salt that is being produced in solution in a flux. There are applications of this in different cases, I will come to that, and when there is not enough heat available, we use something called a booster reaction. There are many reactions possible. The one booster reaction is add calcium and iodine, it will produce calcium iodide, give heat, and this calcium iodide would act as a flux to dissolve this salt that comes out of metal thermic reduction. We have given a flow sheet for recovery of plutonium from spent fuel. Then we have started talking about thorium, which comes from beach sands. The beach sands which are available all along the coastal line of India, or the certain areas in the western coast and eastern coast. Very important deposits are found in Kerala, and our thorium deposits are very big. They are in the beach sands, and in the beach sands there are many constituents. The constituents are mainly first ilmenite, then there is garnet, zircon, rutile, monazite. It is this monazite which has the thorium. We have industries trying to extract TiO2 called synthetic rutile from ilmenite, and we also are taking out the monazite fraction for extraction of thorium. We are not working on extraction of titanium as yet, but the beach sands provide us an important source for TiO2 production and thorium production. About treatment of monazite, a flow sheet has been given. The thing that we need to note is in India, we do not follow an acid leaching process, we follow an alkali leaching process. The peculiarity of which is that during leaching, the metallic values will go into the insolubles, not in the solubles. Then again, if you produce pure TiO2, we talk about reduction by various reductants, and normally we will find this calcium reduction that is most favorable. Now, here TiO2 being reduced by calcium can produce thorium, but if you introduce some calcium chloride in it, then the CaO produced by the reaction of calcium and TiO2 will dissolve in calcium chloride. So, the activity of CaO will go down, the reaction will be driven to the right, made more feasible. I have talked about the importance of zirconium. Zirconium is used as a cladding material in the reactors. A cladding material is where the fissionable material is kept, and when during fission neutrons are emitted, this cladding material will allow them to pass from one tube to another tube. So, in the pile they can go from one place to another without being absorbed and being lost. That's, and also zirconium is ideal because it retains strength at high, not zirconium pure, zirconium alloys. It will have high temperature resistance. It will not be, it will be able to withstand irradiation. It will not be corroded, and so there are many advantages. Now, during a nuclear fission reaction, what happens is a mass splits into two nearly equal halves which go in two directions with high velocities. Small amount of mass is converted into energy. High velocity neutrons are emitted, and if these neutrons can have face four possibilities. They may escape additional fissile mass. No, they may encounter additional fissile mass producing more neutrons. They may encounter fertile atom, produce a fissionable atom like from U-238 to U-239. They may encounter some other atom without any useful result, or they may escape altogether. Now, sometimes we need moderators to slow down the velocity of these neutrons so that they do not escape altogether. And for a given mixture of fissile and non-fissile atoms, there is a certain critical size beyond which the proportion of neutrons that escape is so reduced that condition for a nuclear reaction to take place is attained. Zirconium alloys, which have low capacity for absorbing neutrons, allow the pile to be kept as small as possible. I have given flow sheets for production of zirconium oxide from zircon, production of zirconium sponge and reduction of powder, and then we have discussed beryllium, which is also a highly reactive metal. Beryllium oxide, if reduced by carbon at sufficiently high temperature, will produce beryllium, but that will have carbon in it, because beryllium carbide also forms. Now, to avoid that, if we introduce copper in the system, then instead of beryllium we produce copper beryllium alloy, and because the beryllium activity is low, this reaction will go to the right, will take place more favorably, and the advantage is copper beryllium alloy finds application in the industry. So, we have many advantages through the presence of copper. Free energy change for the reaction is made more negative, reaction moves to the right. The beryllium activity being much low, beryllium carbide does not form, and copper beryllium that we produce finds application in industry readily. Here the beryllium percentage actually is very small, it is mostly copper. Titanium needs special importance, emphasis, because it is a very important metal. It has many properties that attract all metallurgists, very high strength to weight ratio, nearly double that of steel, then corrosion resistance better than 18H stainless steel. They retain strength even at high temperature, show less creep. So, titanium aluminum alloys have become must in aerospace application. They are used in jet engine components, airframes, missiles and spacecrafts. But we are not producing titanium, because the technology is not that easy. Now, I mentioned that India has ilmenite, and given the analysis of two sources from which we can get ilmenite, these are beach sands. They can be very easily upgraded, because ilmenite is easily attracted by magnets. So, using low intensity magnetic separation, we can make a concentrate. And then there are three basic approaches to get titanium from TiO2. We are not following any of them, but internationally one can go straight for smelting in an electric furnace to produce pig iron, because it has FeO. There the iron value is recovered. Titanium goes into a slag, titanium. So, from which we have to produce a halide by chlorination. By acid leaching, one can take out TiO2 in solution, but then the iron part is wasted. If we go for selective chlorination, remove FeO as a volatile chloride, then also the iron value is wasted. But ultimately, excuse me, in these two routes, the idea would be to produce a chloride, titanium tetrachloride vapor, and then from that TiCl2 vapor produce titanium either by magnesium reduction or sodium reduction. Now, I have given a simple example as to how to show that if you consider TiO2 2Cl2 reaction and analyze it thermodynamically, we will find that without carbon there is not much conversion, but if we bring in carbon in the system, then this reaction goes far more to the right and there is lot more conversion. Reduction by magnesium is molecular in nature, but it is easier, it takes place at a lower temperature. The product will be powdery, it needs subsequent vacuum melting and for consolidation. Sodium reduction has a very interesting feature, that it is essentially electrochemical in nature, and that is why we get a good product, but in the industry sodium reduction is not very popular. Essentially magnesium reduction is what is used, and then whatever we get, the thing would have to be consolidated. I ended that module by talking about magnesium electrolysis and sodium electrolysis. There I mentioned the special features of the electrolytic cells which ensure that the metal released does not react with chlorine. In the case of magnesium, chlorine is released, here it escapes, magnesium floats up, it never comes in contact with chlorine. In the case of sodium, chlorine is relieved in the central graphite anode, it escapes from there, magnesium goes out, goes into a annular chamber where, because it is light, it rises and hydrostatically it is taken out, separated out. This is for sodium. So, actually the sodium never gets to react with chlorine. As regards precious metals, the point to note is that here they are valued because of many factors. There is of course some utility value, but more important is they have ornamental value, prestige value and exchange value. Gold has become a standard for financial conditions of all countries. This has the highest exchange value, not so much as utility value, but because it shines forever, it is attractive, it has ornamental value, it has prestige value. Now, we have talked about the interesting properties of gold, which makes it possible to make fine foils and plates. It goes for jewelry making. To some extent that is true for silver also, platinum also. Silver has perhaps more utility value because of its very high electrical and thermal conductivity. It finds application in electroplating, photography, reflectors, dental alloys, all kinds of things. And silver has to be there in gold to harden it. And silver and copper can produce a range of colors from yellow to green in gold. As regards platinum group metals, they have the advantage of very high melting point, resistance to corrosion and oxidation, and in some special applications we need them. Without them it is not possible to melt salts and slags, which have high melting points and which are very corrosive. There are other attractive properties also, which make them find special applications in making thermocouples, in containers that need high temperatures, etc., etc. I have shown a relative abundance of these precious metals, and I indicated that platinum actually is relatively quite abundant as compared to say gold and silver, yet its price is more. There are many reasons for it, because extracting platinum is not easy. I have talked about the cyanidation of gold earlier, I will not do that again. We are following gold extraction in Kolar gold fields through the cyanidation route. Silver can come from some ores which have a mineral called H2S, Ag2S or some other thing which are not very stable, but it also is obtained from ores of lead, copper and zinc. It comes in the slimes during copper electrorefining. It enters lead bullion, and that lead bullion is the most important source for recovery of silver using Parkes process, which needs addition of zinc to molten lead. I have talked about extraction of platinum group of metals from sulphide deposits of South Africa and copper nickel deposits in Canada and Russia. I would not go through that now. I have talked about the importance of secondary metals, the metals recovered from scrap, and once you recover that, we not only clean the environment, we get an access to metallic value where there is lot more metal than we have in ores and minerals. And if we can recycle more and more scrap, then we do not have the depletion of primary sources, and obviously producing the secondary metals would require less energy than producing it from the primary sources. Having discussed all that, I also talked a little bit about extracting some metals from metallurgical wastes and treatment of metallurgical wastes. That is a subject which can be discussed in this module also on energy and environment. I have delivered a number of lectures for this module, because I thought this subject is very important today. And I have also said many things not directly related to non-ferrous metals extraction. I believe the things I have said are important, and anybody who is in a manufacturing industry, or especially if in a metal extraction industry, should be aware of those issues. So, our learning objectives were fairly wide in scope: importance of energy and environment. Then I have talked about cost of development, that when we manufacture things, when you have an industry operating, we want to develop the society by making available goods and services. We have to pay in some other way for that. That is the cost of development. And to understand that, we first have to think what exactly is meant by pollution, contamination. So, I have defined a number of terms, starting with waste, then industrial waste. We have discussed why we are generating wastes, because as our population grows, as there is demand for development, there is demand for production to increase. When production increase, necessarily there will be environmental pollution. unless you take extraordinary precautions. And all that we are doing is coming by exploitation of resources of materials that are available on the crust of earth, which is a few kilometers thick. Below that, as of now, we really cannot go. So, I went back to the relative abundance of metals to show which all metals are abundant, and we found some 8 metals account for more than 95%, and yet metals which on an average are not so abundant, we get them. Why? Because they are concentrated in certain pockets. Had they not been concentrated, if all elements were uniformly distributed on the crust of the earth, it will be very difficult to produce certain metals. Now, the important thing to remember is, if you talk about production of hazardous waste in various industries, industries connected with metal production or metallic products generate the highest amount of hazardous waste as compared to other industries like food and beverages, textiles or wooden products, paper, transport, other machinery. So, the metal industries have to take special precautions. Just to give an example, the biggest culprit in non-ferrous sector is the aluminum industry, which sometimes produces 2 tons of red mud for each ton of aluminum. This red mud as of now is really a waste, which is dumped in ponds that occupy large areas. We are not getting the land then for other uses, and red mud can also, because it has alkali, have adverse consequences in the surrounding areas. There I have given some figures about approximate waste generated by selected non-ferrous metal industries. I have shown how just the 1 or 2 industries is discharging so many pollutants in the land and rivers all around. I went on to define the word pollution, air pollution. I have given a very good definition given by Engineers Joint Council of USA, where they said air pollution is the presence in ambient atmosphere of substances generally resulting from activity of man in sufficient concentration present for sufficient time and under circumstances which interfere significantly with comfort, health and welfare of persons. So, comfort is also included, or with the full use of enjoyment of property. So, when you talk about adverse effect, you are not talking about adverse effect only on humans, animals, plant kingdom, property, everything is included. We also talk about comfort and enjoyment. I have talked about the general adverse effects on health because of pollution problems. Then this is important. I have shown that in all activities in metal extraction processes, starting from raw materials to secondary materials processing, we are generating all kinds of wastes, some of which are toxic, some are not toxic, but the total volume is very large. And when we are generating all this, we are creating an adverse impact on the society. And these impacts, if we analyze properly, we will find what is the financial implication of those impacts, impact on health, impact because of loss of agricultural output, loss of livestock carrying capacity, etc., etc. And then I invoked the concept that if you are talking about a GDP, you have to take it out from that many things, defensive expenditure on defensive steps, expenditure on restorative steps, damage to capital, etc., etc., and then we should calculate a gross ecological product. And if we think of the cost of all kinds of damages to health, human health, animal health, plant health, we talk about ecological damages, etc., we may see that when we are talking about a growth, it may be actually a negative growth. Not many people are aware that many such analyses have been done. They are debatable, no doubt, but the central idea is very good. You are talking about progress, but you have to pay for that progress, and sometimes you have to pay very heavily. I have given some figures. Again, I said they are debatable, that in the 90s somebody showed that we were claiming more than 5% annual growth rate in GDP, but it was actually a minus figure if you took into account all the cost of the development. So, how do we handle the situation? For that we have to be smart. We have to think of ecologically sustainable development, that okay, we have development, but it must be sustainable ecologically, and that is defined as that you enjoy life, but you also ensure that your future generation also enjoy the kind of life you are enjoying. So, like if you have a bank balance, you live on the interest, not on the capital. I have talked about carrying capacity, the sustainable development. Then I have talked about analyze what we mean by development, and for sustainable development we need to go for reuse, reduction of material use, recirculation, both for materials as well as energy. And we have to be aware of certain terms like life cycle assessment, end use assessment, and after we have done that, I have given you some guidelines as to how in the industry they introduce environmental policies, what are the procedures they need to adopt, what are the environmental aspects they have to consider, and how they can quantify the effect on environment and using some criteria, and in terms of area affected, severity, duration, frequency, and give a total score, because one you have a high score, you have to be more careful. Then something about waste management, environment management system and environment management audit I have discussed, how we should produce in an industry. I have taken example of the aluminum industry and mentioned what is a local effect, what is a regional effect, what is a global effect, given some more details. And finally, I ended up by saying a few things which have been the basis of discussions in Copenhagen and Denmark recently, that we have to do something about CO2 emission. Various countries are setting various targets, mostly voluntary. We still haven't got a legal framework, and everywhere we had this talk about carbon footprint that has to be reduced. People want to get carbon credit, and I have said it is possible to be smart and progress without increasing per capita energy consumption. And finally, I have ended my lecture by saying that the time has come to very seriously think about making use of alternate energy sources, better technologies like high pressure grinding rolls. Grinding takes 3 to 4% of the energy use of the whole world. In the mineral industries, copper industry, 75% of the energy goes for grinding only. So, you must have better techniques, and I have given examples of how energy can be saved. Then I have given 2-3 problems to discuss the concept of life cycle assessment, and I have ended by some remarks on nuclear reactors, because some countries are getting their energy supply, electricity supply by using nuclear reactors, and we have to depend perhaps more and more on nuclear reactors, because then we will have a CO2 free source. Not nuclear reactor, there could be many other alternate energy sources. So, friends, I have done what I could in the course of these 40 odd lectures. I hope you have got some idea about the basic principles of non-ferrous extraction and basic features of extraction of various metal extraction processes. I hope you are enthused enough to go back to some books and read more about these things in the literature that is available. Thank you very much.